Welcome to the first part of our three-part video series on LLM, RAG, and MCP, three powerful techniques that are modernizing the way we build robust AI systems. In this series, we explore how these technologies work individually and together to create intelligent, scalable, and context-aware solutions. Hello everyone, welcome to my channel Cloud, Container Code, and AI, where we explore the world of cloud and AI. I'm Gautam and I bring over 20 years of experience in designing, managing, and supporting Microsoft enterprise services. Today, we are kicking off the first part of our three-part series, the focused on getting more details on AI system like LLM, RAG, and MCP. Though we will slightly touch the RAG and MCP, but second part and third part I will cover RAG and MCP in details. First, we'll see the large language models. The LLM at the core responsible for generating human-like text based on input prompts. RAG, we know already, retrieval augmented generation. RAG enhances LLM by retrieving relevant documentation from external sources to ground responses in factual data. The MCP, the Model Context Protocol, the MCP is an open protocol that standardizes how applications provide context to large language models. Think of MCP like a USB-C port for AI application. Just as USB-C provides a standardized way to connect your devices to various peripherals and accessories, MCP provides a standardized way to connect AI models to different data sources and tools. MCP enables you to build agents and complex workflows on top of LLMs and connect your models in the world. In this video, we'll take a deep dive into large language models, where we'll explore the key components of LLM, their architecture, how these models are trained, the real-world use cases, and finally, the evolution of LLM over time. So let's get started and unravel the power behind today's most advanced AI models. So let's go in detail. First, see what is large language models. The LLMs are deep learning models trained on massive datasets of text. They are built using transformer architecture, which allow them to process and generate languages in a way that mimics human communications. Example is like ChatGPT, Claude, Gemini, and Llama. They are called large because they contain billions to trillions of parameters, the internal settings that help the model learn patterns in a language. The key component of large language models, the first is massive datasets. The LLMs are trained on vast and diverse text corpora that can be books, websites, articles, and tools to learn rich language patterns and semantics. The transformer architecture, the foundation structure of LLMs is transformer architecture, that using self-attention to model complex relationship between words in context. The tokenization that converts raw text into small units tokens, enabling the model to process and understand language efficiently. Attention mechanism allowing the model to focus on most relevant parts of input, improving coherence and contextual accuracy. The positional encoding that adds sequences awareness to the model, helping it understand the order and structure of words in a sentence. The fine-tuning that adapts the pre-trained model to a specific task or domains, enhancing performance and relevance. Scalability, with billions of parameters, LLMs can handle complex, multilingual, and domain-specific tasks at scale. So now, next, LLM architecture. So here we'll just see the transformer backbone, how the transformer architecture is working. The core of LLMs is the transformer architecture, which revolutionizes natural language processing by enabling parallel processing and deep contextual understanding. It uses self-attention to evaluate relationship between all words in a sentence simultaneously, that allowing the model to grasp nuances meanings. The layers and patterns LLMs consist of multiple stacked layers, often hundreds with billions of trainable parameters and all. These layers progressively refine the understanding of input data, that again enabling the model to capture complex linguistic patterns and semantic relationship. Tokenization, which already know, we know that is raw text is broken down into tokens that can be words, subwords, or characters. So the model can process language in manageable units. This step is crucial for handling diverse languages and vocabularies efficiently. The positional encoding, since transformation process tokens in parallel, they lack inherent sequence awareness. Positional encoding adds unique vectors to each token based on its position, helping the model understand word order or sentence structures. Attention mechanism, self-attention allows the model to weigh the importance of each token relative to the others in sequences. This mechanism is key to understand context, resolving ambiguity, and generating coherent responses. The feedword networks, each transformer layer includes 10 feedword networks that further transform token representations. These networks help refine the model's understanding and contribute its predictive capabilities. The output layer, the final layer generation of prediction, such as the next word or a complete response. Based on the learned patterns and contextual understanding, it translates internal representation into human readable text. Now, let's say what is how the LLM training process works. The first process is data collection. The training begins with a gathering massive and diverse datasets from sources like books, websites, articles, and code repo and all. This ensures the model learns a wide range of language patterns, style, and domain-specific knowledge. Pre-processing the collectible, the data is cleaned to remove noise, tokenized into manageable units, and formatted consistently. This is a step ensure high-quality input and prepare the data for efficient model training. The model initialization, this transformer model is initialized with a random weight and configured with a specific number of layers and parameters. This sets the foundation of learning during training. The training phase, this model learns by predicting the next token. In a sequence, it adjusts its intent weights using backpropagation and gradient descent, that gradually improving its understanding of languages. The compute resources, training LLM using powerful hardware like GPUs and TPUs and distributed computing system to handle the enormous computational load and billions of parameters. The fine tuning, after general training, the model is fine tuned and domain specific dataset to specialize in a task like legal, medical, or customer support languages, that improving accuracy and relevance. The evaluation and validation, the trained model is rigorously tested using benchmark datasets and real world scenarios to assess its performance, coherence, and bias. This ensures reliability before deployment. Now we'll see the use cases of LLMs. The first use case is business and enterprise customer support automations. LLMs power chatbots with virtual assistants that handle customers' queries with natural human-like responses. The document summarization automatically condense lengthy reports, emails, or legal documents into concise summaries, in emailing, drafting, and communication that generate professional emails, proposal, and internal communication. Education and research, tutoring and learning assistant provide explanation. Like for example, it is giving the answer of your questions and guide learner across subjects and academic research and all. That assist again in a literature review, hypothesis generation, and technical writing. The language translation here that translates the text across multiple languages with contextual accuracy. The software development, code generation, and debugging. This help developer write, refactor and troubleshoot code in various programming languages and all. So the documentation creation that automatically generates technical documentation for code bases or API. The media and content creation again, and then again it is very much beneficial for healthcare medical documentation as well. And wherever the legal and compliance contract analysis and all is required, where large number of contracts or legal terms you need to understand, but the large language models is extract the key clauses, summarize terms, and flag potential risk. That is helping in regulatory research, and again it's a help legal team stay updated with changing laws and regulation. So now see the evolution of LLMs from GPT-1 to GPT-5. This journey begins with GPT-1 in 2018, introducing the transformer architecture. Each generation since has dramatically increased in scale, capability, and contextual understanding. The scaling parameters from GPT-2 that had 1.5 billion parameters, GPT-3 jumped to 175 billion parameters, and GPT-4 introduced multi-model capabilities. GPT-5 now integrates multi-model reasoning with over 2,000, I would say 256K and maybe 300K tokens of context. That again jumps from few shots to zero shot learning. Early model requires example to perform task. Modern LLMs can now generate from instructions alone, enabling zero shot learning. The multimodal intelligence GPT-4 and GPT-5 can process text, images, and even audio, making them versatile across domains like healthcare, education, and software development. The safety and alignment. The neural model are trained with reinforcing learning to improve safety, reduces bias, and align better with human values, where it is completely matching other responsible AI principles like inclusiveness, privacy and security, accountability, transparency, and all. The real-time interaction GPT-4o and GPT-5 offer faster, more natural interactions, making them suitable for real-time application that like virtual assistants and live translation. Large language models, RAG and MCP, together enable AI to understand context, retrieve real-time data, and act intelligently, transforming business workflow with smarter adaptive automation. And it is beneficial, and it is increasing the day by day the importance of AI. In second part and third part, I will present the details of RAG. Till the time, take care and keep learning. Thank you.